Hi, welcome to this last installment in our series dealing with limits. So this is basically a recap. We're going to look at using three methods to solve limits, and then we will return to our initial gradient problem. Substitution is by far the easiest method that can be applied to solving limits. It's not always possible to use this method. If you have an expression and you need to solve some limit and it's not solvable using this method, then the strategy to employ is to somehow manipulate that expression so that you can apply this method. So let's look at this polynomial here. So remember, polynomials are continuous for all values of x. So here we need to find the limit as x approaches 3 of this expression. Well, this is quite straightforward. You simply substitute 3 for x. And so we get 3 squared plus 8, 17. So the limit of this expression as x approaches 3 is 17. Here we ask to find the limit of this rational expression. If you tried simple substitution, you'd end up with this indeterminate form. Whenever you end up with indeterminate forms, that's always a clear indication that more manipulation is required. And that at the end of this manipulation, you will either get some finite limit or you will determine that the limit doesn't exist. So in this case, what we do is simply factorize these expressions. So if you don't remember how to factorize these, you need to go back and look at maybe an intermediate algebra course. So this factorizes to x plus 5, x minus 3, and this is a difference of squares, so this factorizes to x minus 3, x plus 3. Of course, this then can be simplified. X minus 3 divided by x minus 3 gives us 1, leaving us with x plus 5 over x plus 3. And the limit of this expression now as x approaches 3 is 8/6, which is the same as 4/3. So the limit of this rational expression as x approaches 3 is 4/3. Notice this is not defined for x equals 3, but that's not the point. We're not interested in finding what f of 3 is. We're interested in finding the limit of this expression as x approaches 3. So by now you should understand the distinction very clearly. Once again, direct substitution would lead us to this indeterminate form. What we can do in this case is multiply both the numerator and denominator by the conjugate of the denominator. So the conjugate of square root of x minus 3 is the square root of x plus 3. Note that this expression here is equivalent to 1, and so if we multiply something by 1, the result is going to be an equivalency. This here, we can multiply out the denominator and we see that we get x minus 9, and up here we get the product of these two expressions. Simplification is possible here. X minus 9 divided by x minus 9 gives us 1, leaving us with this. And of course, now we can apply substitution directly. The limit of this expression as x approaches 9 is going to be 6. Square root of 9 is 3, plus 3 gives us 6. So the limit of x minus 9 over square root of x minus 3 as x approaches 9 is going to be 6. We have been studying limits for a while now, and we should be fairly proficient at finding the limits of expressions. So let's apply this knowledge now to our original question that we looked at in the first video named Y limits. In that first video, we looked at the question of trying to find the gradient of a line drawn tangent to some function in terms of that function. So that is the key issue. We don't want to just draw this line tangent and then measure the gradient, using graph paper or something like that. We want to be able to use that function itself to get the gradient of this tangent line. However, there is no way to do that directly. So what we suggested was that instead of finding the gradient of this tangent line directly, what we do is we find the gradient of a secant line, which cuts this function at 2 points. Why? Because then we can find expressions for these segments in terms of this function. So this point here is simply some x, and this is what f of x. And this point is, well, what's the value of x here? Well, it's x plus h, and the y value is f of x plus h. To get the gradient, we need to know the rise over the run, and so the rise is just going to be the change in the y values, f of x plus h minus f of x, and the run is going to be the change in the x values, so that's going to be x plus h minus x, leaving us with just h. So dividing this, the change in the y by the change in the x, gives us the gradient of the secant line. But if we are able to go reducing this horizontal displacement here, we see that as h approaches 0, the gradient of the secant line approaches the gradient of the tangent line. So let's apply this to a concrete example. Here we're given the function f of x equals 5x squared, and we're asked to find the gradient of a line drawn tangent to this function at x equals 3. So what we're going to do is just draw a secant line. We want the gradient at the point x equals 3, so this point then becomes 3, 45. Why? Because, well, f of 3 is 45. Notice it's 5 times 3 squared, 5 times 9, 45. Then we come over to another point on the graph of the function. So we come over what? An amount h. Now in this example we have come over h is 2.07, but we're not really interested in those values. I just put them here so you have something to anchor yourself on. So we come over some h, and so this coordinate will be 3 plus h. And what will the y coordinate be? Well, it will be f of 3 plus h. So wherever I see an x in this function expression, I put 3 plus h. So then it becomes 5 times 3 plus h squared. If you do the calculation, you'll see that this point then turns out to be 5.07, 128.52. So now let's find the gradient of this secant line. And the gradient of the secant line is simply going to be the change in the y, which is 5 times 3 plus h squared minus 45, divided by the change in the x, which is 3 plus h minus 3, which leaves us with just h. Now, remember we're using the secant line to then determine what the gradient of the tangent line is going to be. So what we want to do is find the limit as h approaches 0 of this entire expression. Now, if you simply substitute, you're going to get 0 over 0. Notice this becomes 45. 45 minus 45 is 0, and this is 0. So the way out of that is to, in this case, expand this expression. So once we have expanded this, we then multiply this by 5 and we get this expression. Again, if you're not following this, you need to go and review some intermediate algebra. So this is just the expansion of the square of a binomial. Of course, once we have expanded this, we have that 45 minus 45 is going to give us 0, leaving us with this expression. And now we can divide out by h, and we're left with this expression. And of course, finding the limit of this expression as h approaches 0 is easy. We get 30. So you need to visualize this. Imagine this point being brought along this graph, getting closer and closer to this point. As that is happening, h is getting smaller and smaller and smaller, and this secant line is approximating the tangent line. As you can probably visualize here, the tangent line is going to have a gradient that's less than this secant line, because obviously it won't cross the line. It will just barely touch this graph at one point and move along somewhere like this. So here we see the line drawn tangent, and of course its gradient is 30. And we were able to determine this gradient without having to draw this physically on some graph paper. We simply were able to do so using the function definition itself. So I'll try and demonstrate this a little bit more. For this demonstration, I'm using an application called GeoGebra. So I'll put a link to this, to where you can download a copy of this application. There are different versions. You can get apps to use on your smartphones if you want. And then there's a classic version to use on PCs. It's a very wonderful application, and I use it a lot to teach mathematics and to teach physics. So I really urge you to take a look at this application. So what I have here is called a slider. And with this slider here, I can go manipulating the value of h. So right now the value of h is 3. So you can see that 3 plus 3 gives us 6. And this is giving me the gradient of the secant line. So the gradient of the secant line for this value of h is 45. So let's go reducing the value of h. So you can see what's happening here. This h is getting smaller and smaller. And the gradient of this secant line is approaching the gradient of the line drawn tangent. So notice as I keep reducing the value of h, so this number here gives me the value of h. The gradient is approaching the gradient of the tangent line. So right now at this point, you can't tell the difference between the secant line and the tangent line visually. And you can see that we are approaching 30. So that is what we're doing when we're finding limits. We're finding the value that some function is approaching as some variable approaches 0. So I hope this little demonstration is helpful. Again, I'll put the link in the description so you can go and get this application. I'll also put a link to this little applets. We like to call these little things applets that we build inside of GeoGebra. I'm sure there are better ones. So if you go to geogebra.org, you can find some really good ones. This is one I made for this little video. So if you like it, you can download it. So I hope that helped you to understand what is going on here. We have this function 5x squared. We want the gradient at this point. We draw a secant line. We get the gradient of that secant line using these 2 points. And then we see what the gradient of this secant line approaches as h approaches 0. And here we see that we get 30. So that's it for this series on limits. I hope this has been instructive. The next set of videos will be about differentiation. This topic that we just covered here, this application, is a lead up to differentiation, because this is what we're doing when we differentiate functions, when we find the derivative of functions. There is going to be a shortcut and a series of shortcuts that we learn as we go along, but it is important that you always understand what it is that the shortcut is cutting short. So that's why we're looking at this, because this is the foundation of all differentiation. You could almost say it for all calculus too. Okay, so bye and thanks for your attention.